Okay, so in this video I will show you how to install and set up the Toychain. The Toychain is a blockchain simulator that helps to run experiments in Argos faster than real time. So in order to install it, I've written a small report here. So it starts with the installation of Argos and the Argos ePub plugin. I've already done this on this computer here, so I will skip this. For the Toychain, there's a final report that a master student wrote who also developed the Toychain, but for the purpose of this tutorial, the report is not so relevant, so I will start here with point 2.4, the installation of the Toychain Argos interface. So I will go to the GitHub repository and follow the installation guide here. So first of all, I will clone the repository. I'll make a new folder here. And then I move into that folder. In that folder there's the Argos Python plugin, so I will install this first. And by the way, in order to install it, you might need some additional software. I've already installed it, but here I will run this again. So here everything is fine. Then I will go back to the folder here. I will run the necessary commands, and here you will already see something that it could not find Boost, but Boost is required for the Argos Python plugin. So this is a problem in the CMake file. It depends a bit on your system. So what I will do here is I will change this line from Python 3.8 to Python 3. And then I will run CMake again. And this time it found Boost. So I can make the software. Let me check here what else we need to do. Yes, just make. And then we need to configure the experiment and update the paths. So in this tutorial here, we will develop a very short hello world simulation. So it will just say hello to a robot whenever two robots meet. And in fact, we will not even say hello. We will just develop a short smart contract where we increase a counter whenever the blockchain softwares of two robots connect to each other. Okay, so now we've installed the Argos Python interface. Now I will go to this hello world example. There's already a bare bone example written there. And now we need to develop it further and configure it to fit our computers. So first of all here I will got stuck here. I will update the experiment config. So the most important variable here is the main folder, or the home folder actually. So we installed everything in home demo. So now, and this is now home demo Toychain Argos, which is correct. And in this experiment file you can set many other parameters, like for example the number of robots that we want to use, but this will be more relevant later on. So I save this and quit. And now I think we're already done, and we can try to start this bare bone experiment. For this there's a file called starter. I'll show it here, and it accepts a couple of additional parameters. We will use this -s here in order to start the experiment with visualization. So I will say starter -s, and this worked, and we have here a very basic setup where the robots move in a square environment, performing a random walk and connecting to each other's blockchain versions whenever they are close to each other. But for now they are not doing anything. So we can also see it here in the command line. All the nodes started mining, or actually they will perform the proof of authority consensus, but they are not interacting in any other way with each other because there is no smart contract yet. And now I'll show you how to develop a very simple smart contract. So usually smart contracts are written in a specific programming language. We are inspired here by Ethereum. So in Ethereum there is solidity, and a smart contract usually looks like that. But with the Toychain we can develop everything in Python. So I will now show you how to do it. So first of all, we need to write the smart contract. For this, I'll open here Sublime. I'll open the demo folder and Toychain Argos. Now we can write the smart contract. This is done here in Toychain, source, and then block. And down there we have the class state. Here's actually still stuff from a previous experiment, so I will remove all of this. And then add our things. So what we want to have is just a simple counter whenever they say hello to each other. So I add this counter, self hello counter equals 0, and then we write a function to say hello. So we just increase this hello counter by 1. Problem here that I think there's a problem with the video recording, that whenever I try to click on the equal sign, it toggles the mouse here. Maybe I can disable this. Yeah, now it works. So we say the hello counter is increased by 1, and we also write a getter here. So we say get hello counter and then we just return the counter. Now this was the smart contract. Now we need to interact with that smart contract in the robot controller. So for each experiment you need to create a separate folder. Like for example here now we have this hello world experiment, and also the market foraging experiment. We want to use the hello world now and go to the robot controllers. So it's in controllers main.py. And there we have the control step here. So first let's define a counter for each control step per robot. So in the beginning we just set it to 0. And this will just help us to keep track of in which tick the experiment currently is. So we run the experiment with 10 ticks per second. And here we have the peering routine. And this is the part here where robots connect to each other. So we say that we use our RAB sensor to check which robots are close to each other, and then we add these robots to each other in the blockchain processes. And simultaneously we also want to say hello to each other, or we want to increase that counter. So what I do here is I write a blockchain transaction. So I want to send a blockchain transaction here whenever two robots connect to each other. So we just say here, say hello, and then we define the transaction data. So we want to interact with the function say hello. We don't need any additional inputs. Now I create this transaction. The sender is the robot itself, so it's me.id. The data is this transaction data. And now we send the transaction. It's done with this W3, shortcut for Web3. And we send it. In addition, we want to retrieve the number of times robots said hello to each other. So for that we just say whenever this counter that we defined in the beginning is at a multiple of 100, we have printed out how many times the robots said hello to each other. So in order to make it a bit more verbose, we say the robot and then the robot's ID, hello counter is, and then we retrieve information from the smart contract. So this is done with w3.sc for smart contract, and then we use this function get hello counter. And at the end of each control step, we increase the counter by 1. Okay, I think this should get us started. So I will try it out now. I will restart the experiment, and I've made an error here. So I'll try to stop it as soon as possible. Here I forgot to add an equal sign. So this was here. Okay, let's retry. Okay, again an error. It has no attribute get hello counter. Let's see what I did wrong here. I have defined get hello counter. Okay, so in the meantime, I think I figured out what was going wrong. So there was a wrong indentation here. This needs to go here on the same depth as this init here. So I will save this and try to restart the experiment. Okay, and this time it works. So we see the robots are still performing exactly the same movements and control loops. So they are having this random walk and then they are close to each other. They connect to each other's blockchain processes indicated by this blue line here. Now if we go to the console, we see that this hello counter is increasing. And we have these 6 robots here, and for example here we see that the counter of some robots is here 3, of some others is 4. So here it's 12 for all 6 robots. And importantly, what we see here, this number here is not always the same for all robots. So this hello counter is a global variable, but not all robots always have the same state of the blockchain because of forks. So the robots that have already received the newest blockchain version have higher numbers here, for example already 46, while some other robots are maybe disconnected from the swarm, as we see here. Now these 2 robots are not connected to the majority of the swarm, so they will have blockchains that are at a lower blockchain height, and therefore also their number is lower. Okay, so this was all for today and for this tutorial. So it just showed you how to write a very simple smart contract, and if you want to make it more elaborate, more sophisticated, you would just write more complex functions here in that state class and then interact with them in the control loop or the control step of the robot's controllers. Thanks for watching.